Reduction of monosaccharides. Aldoses and ketoses can be reduced with sodium borohydride to compounds called alditols. So you take aldose, add some sodium borohydride or H2PT, that means hydrogen in platinum, or even you can take palladium. So you will get alditol, where this CHO group will be converted into CH2OH group. Reduction of D-glucose, for example, it's D-glucitol. So this is your D-glucose and you are reducing it with sodium borohydride, you will get D-glucitol. If you take D-galactose, you will get galactitol, which is also called dulcitol. So this is the dulcitol. Now take beta-D fructopyranose, then this is in equilibrium with its open chain form, and then reduce it with sodium borohydride, you will get both the glucitol and mannitol. That means sodium borohydride basically supplies the hydride ion H-. So if this H- attacks from this side, you will get this mannitol, and if this H- attacks from this side, so this OH will become on the right hand side, so you will get glucitol. Which monosaccharide is reduced to give the same product as that of D-glucose? So you have the the structure of D-glucose, so you know the alditol structure, the glucitol, this one, and you are asked that which other monosaccharide will give the same alditol after being reduced, and the answer is the L-glucose. If you take L-glucose, then if you reduce it, you will get the same alditol. How to get to the answer, I will discuss it later. Oh yeah, I have discussed it here. Easy method to find out. At first, draw the given molecule with Fischer-Allowed 180-degree rotation. So this is your structure. If this is your glucose, that means here it is said that which monosaccharide is reduced to give the same product as that of D-glucose. So you know the structure of D-glucose. So first draw the D-glucose. Then just rotate it in plane 180-degree rotation. That means this top will come to the bottom and this bottom will go to the top. Just 180-degree in plane rotation. So you will get this, and in the next step just cut it down and replace these two. This CHO group will come here and only this CH2OH group come here. So you will get this structure, which is actually L-glucose. As the former was D, this was D, after rotation it will convert into L, so this one will become L. This is the L-glucose. Explain why sodium borohydride reduction of D-fructose leads to both D-mannitol and D-glucitol. Reduction of D-fructose creates a new asymmetric carbon atom formed in either of two configurations, and so two diastereomeric products are formed, which I have just told you that this sodium borohydride can attack from this side or can this side. As this is a new asymmetric carbon, it can give two diastereomer, this one and this one. Reduction of aldoses by concentrated HI, that means hydroiodic acid, and red phosphorus. If you take the alpha D glucopyranose, this is the open chain form of D glucose, and then if you give HI red phosphorus, these all OH groups will be converted into hydrogen. So you will get N-hexane. So this one will also be converted into CH3. This CH2OH will also be converted into CH3. A ketohexose cannot be reduced to the corresponding alkane directly by concentrated hydroiodic acid and red phosphorus. However, on successive reduction with sodium amalgam and HI red phosphorus, they form the corresponding alkane. So you cannot use the HI and red phosphorus with the fructopyranose. At first you have to use the sodium amalgam, then you can reduce it with hydroiodic acid and red phosphorus. So you will get the N-hexane.